Okay, so I'll introduce.
So we're very happy to have Joni, and we will talk about entropy decrement argument applications.
Thanks, Tammy. Yeah, so I'd like to explain to you Tao's entropy decrement argument. So this is a tool that Tao developed for his proof of the two-point Charlotte conjecture with logarithmic averaging. And since then, it's been used in essentially all the progress made on Charlotte's conjecture, and also some of the progress on Seiberg's conjecture. So I'd like to explain this method to you and detail one application, namely Tao's two-point Charlotte, how the entropy decrement argument can be used for that. And it's a fairly general method. So one could hope that there's also other applications that don't have to do with correlations. So hopefully something like this will emerge. I'd be happy to hear if one of you has some applications that you come up with. Okay, but let's just start by listing a few applications of the method before we talk about the actual method, and starting with the initial one for which Tao devised this method. So this is his two-point Charlotte theorem. The sum of level of n, level of n plus 1, divided by n, is the rule of log x, as x goes to infinity. And just to recall, the level function n is -1 to the total number of prime factors of n. So omega n is the number of prime factors of n with multiplicities. Okay, so this is Tera's two-point Charlotte. And so the same entropy decrement argument was also an ingredient in the proof of Tera and I when we proved the odd order cases of Charlotte.
Maybe just two-point logarithmic Charlotte.
Yeah, it's logarithmic, yeah. One needs the logarithm of everything.
Yeah.
Otherwise it's not. No. Yeah.
It's omega n. It's okay. It's omega n.
Yeah. What about that?
So
It's the number of prime factors.
I think we did come with multiple.
Yeah, with multiplicities. Yeah. Yeah. Sorry. It should be. I guess. Yeah. P to the alpha totally divides n alpha. Yeah. Thanks.
Otherwise, maybe
Yeah.
it's
Okay, so we use the same method to prove the odd order cases of the logarithmic Tau connection. So if k is odd, then we prove that the k-bond correlation of the Liouville function with logarithmic averaging tends to 0. Okay, and let me also mention an application to Seiberg's conjecture. So the transcendental is host ratio on Seiberg. Also use the entropy decrement argument among many other interesting ideas. So this one says that if you have xt is a topological dynamical system, zero entropy, and if you have at most countably many invariant ergodic measures for this system, then you have some exponential with logarithmic weight. So if you have this, then for any observable in the system, you have the logarithmic sum for every y and x, and for every continuous function on x. Okay, so this is a sample of the kind of theorems for which the entropy decrement argument is useful. So in this talk, I want to focus on the first one, the one that originated the method, so the 2-point Java. And okay, so there's 3 main steps in task proof of 2-point Java with log weights. So one of them is the entropy decrement argument, but the first one is just using the multiplicativity of the Liouville function. Obviously, you want to use that. So that is so the purpose of that is to add an extra variable to your sum to make it more manageable. So at the moment, if you look at that average there, it's of the same difficulty as the string prime project. So if you try to attack it directly, because you're counting consecutive integers that have a given value of the Liouville function. So you can do that directly. But so the first thing is to use multiplicativity. This allows you to add an extra variable to your correlation. The second step is that, so initially, these 2 variables that you get, they're going to be highly dependent on each other. So you would like to somehow decouple the variables. That would be a lot nicer than you could do things if you have 2 independent variables in your sum. So for that, you have a kind of sampling inequality. I'll explain that later. The proof of this sampling inequality uses entropy decrement. Okay, so this is a key step. And then the final step is that now that you have separated your 2 variables, essentially what you end up counting is how often Liouville of n is 1 and Liouville of n plus p is 1 for a prime p. So you're counting n and n plus p having an even number of prime factors. For that, you can use essentially the mathematical Rogerview theorem. On the Liouville function in very short intervals, so typical very short intervals. And so number 2 was the main new ingredient in task proof. So let me first explain how step 1 goes. Okay, so let's call this sum S. Or maybe let's do let's divide the log x p other side. So s is 1 over log x, sum of level of m, level of m plus 1 over n. And take some function p of x.
Give me 1 over log n. Wait, sorry. The sum is up to x does not appear in the sum. Is it some? Sorry, is that sum not to x? Oh, sorry. Your x just looks like a lambda. Okay.
Okay, so take some function p of x, which tends to infinity slowly. Think of something like double log x, let's say. So p of x is something like double log of x. And now use the multiplicativity. So for any prime p less than p of x, we can write s as, we just artificially add p of n here to the summation. So lambda of p of n, lambda of p of n is p over n. Okay, so that's because lambda p is -1. And so then some variables. So if I write m equals p times n, and the sum becomes 1 over log x, sum of m up to px, level of m, level of m plus p over m, and then we have the condition that n must be a multiple of p. So p indicator p divides m. Okay, so here we already have two variables. So we have the m variable and the p variable. But there's two things that are problematic. So there's a slight problem that the summation length depends on p as well. So let's fix that first. So we want to make the summation length independent of p. For that, we use the logarithmic average. And that's the only part in the whole proof where logarithmic averages are needed. So if you have a logarithmic average from up to 2x, it's almost equal to the logarithmic average up to x, because the logarithmic measure of the interval from x to 2x is small, so it's literal 1. And similarly, if you have a logarithmic sum from x to px, where p is small compared to x, the contribution from the interval is small. You don't use anything about the Liouville function. That's the measure of the interval in logarithmic sense. So you can just truncate the sum up to x. And put the contribution from x to px to an error term. So you get the logarithmic measure of the interval from x to px, which is equal log p over log x. So in particular, that is going to 0. So it goes to.
So for this, you don't need p of x to go so slowly.
Yeah, it doesn't need to go that slowly, really. Yeah, you just need p of x to grow slower than any power of x. Yeah, that will be enough. Okay, so this term here is just log of 1. Okay, so now we fix one of the problems, but the main problem with this expression is this annoying factor of p indicator p divides n. So it highly couples the two variables. it would be much nicer if you could just ignore this factor. You would have just a sum of lambda m, lambda was p. And then after averaging over p, you could do something with this. Okay, maybe let's first add the average over p here before we worry about what to do with the indicator function. So we can write S, the sum of so average over the primes of px. So log 2, by log 2 I mean the second logarithm, so log px. And I just substitute what we had before for the correlation. Okay, so if we just sum over all the different primes up to px with 1 over p weight and substitute the result we had before, we get this kind of expression. Okay, and so we want to get rid of this coupling of the variables somehow. And okay, so you could think that, well, the Liouville function or its shifts, so this expression should not really correlate with an indicator of a divisibility condition. So there should be no correlation between the kind of the signs of the Liouville function here and whether m is a multiple of phi or not. So these should be independent events, at least you expect so. And therefore, you would kind of hope that you can take the average over p separately. So if these two were genuinely independent, you could take the p average separately. So you would just multiply the p average of this term and the p average of this term. And what is the p average of, sorry, the m average? So if you could take the m average of this one times the m average of this one. And so what is the m average of p indicator p divided by m? Well, that's exactly 1. So there's probability 1 over p that p divided by m and you multiply it by p. So if you could separate the two averages, then this would average out to 1, and you would not have to worry about this factor. Okay, well, doing that rigorously is going to require work, namely that's the step 2. So in particular, entropy decrement. But let's for now just see that what if we could do this? So if we could delete the p indicator p divided by m factor, how could we proceed to finish the proof? And then let's return to how we actually get rid of the coupling of the variables. Okay. So this was step 1. And let me just say the step 2 is going to be the proof that the same expression, but with a -1 here, is going to be small. And I'll return to this step later. Okay, and let's move on to the final step. So now we want to understand the expression without this divisibility condition. And so the logarithm of everything is not important anymore. So let me just get rid of that. So by partial summation, it suffices to prove an estimate for the ordinary average. So it essentially suffices to prove that if you take the same average, but without the 1/n weights, this is little of x times number of primes in sum. So if you can prove this for the unweighted averages, you can also prove it for logarithmic averages. So let me just ignore the logarithmic weight from now on. Okay, so let's study this expression. And let's recall a tool that Terry had available when he proved this theorem, and the one that he used, so the Mathematical theorem. So this was also a crucial ingredient. So it says that if you look at short sums of the Liouville function, so we have a short interval of length h, and we average over the different intervals. And this is little o of true about s times x. Provided only that h tends to infinity with x. Okay, so you can take very short intervals whose length tends barely to infinity, and on almost all of those intervals, we understand the short sums of the Liouville function. Okay, so how does this relate to what we have? Well, let's first pretend that our sum over p here is actually a sum over the integers. Okay, so what if the p sum was just over all the integers up to px? So then we could write, and of course we can't do this, but let's just pretend that. So if p sum was over integers rather than primes, then we would have the sum of, let's say j is the integer, and now I change the order of summation, so change the n of j sums. Like this. So now the inner sum is a short sum of the Liouville function of length p of x. around some point n with a size at most x. And to this setup, you could specify the mathematical regressive theorem. So bound this by in absolute value. By the sum of Liouville over intervals of length px. And then the mathematical regressive theorem, if you make a change of variables, it exactly tells you that this is small. So this would be a little of x times px. Okay, so things would be very well for us if the sum was over the integers. That's the conclusion. Well, it's not over the integers, so you can do still get the primes. So what you can do is to treat this sum here as a general average over kind of progressions or patterns. So we're sort of counting how often Liouville of n is 1, Liouville of n plus 1, n plus p is 1, and p is a prime. So we're counting patterns n plus p weighted by the Liouville function. And so one can prove that if you have an average of this form, and so it doesn't matter that this is the Liouville function. You could have any bounded functions here. You can always replace this by a sum where the p is essentially over integers, but actually need rough numbers, so integers with no small prime factors. So we can make the t sum a j sum over integers with the GCD of j as a number being 1. J, and we need a normalization factor, so w over the phi function of w and log of px plus little o of x at the number of primes of the px, where okay, so what is w? It's the product of primes up to little w, where little w is a parameter you can choose. And so, of course, this w refers to the w trick. And okay, so what we're claiming here is that the such a sum over n and p can be replaced by a sum over n and j, where j is not quite an arbitrary integer, but it just needs to be co-prime to small numbers. Let's say numbers up to 1 million or something. Okay, so this is a general fact. You could just replace Liouville function by anything bounded. And so in a more general setting, this would follow from the Green-Tau-Ziegler linear equations in primes theorem. So if you know the Gauss norms, you could recognize this as counting patterns n plus p, weighted by the Liouville function. And then because the primes are Gauss uniform compared to the indicator of rough numbers, you could just replace the primes by rough numbers using the generalized von Neumann theorem. But actually, because this is just It's a very simple pattern. It's a complexity 1 pattern. There's also a simpler, more elementary argument, which is that you use Fourier analysis on this expression. In other words, you use the circle method. And so if you use Fourier analysis on this expression, you get an exponential sum of the primes, in particular, an exponential sum of the Liouville function. But the exponential sum of the primes, you can show that it's almost equal to the exponential sum of the W rough numbers. Because if you're on the minor arcs, both of these sums are small. And if you're on the major arcs, they have the same main terms. And therefore, on the Fourier side, you could just replace the primes by this indicator of rough numbers, and then rewrite your expression again in this form, and you will get this. Okay, so we have now reduced the average to something simpler, and now we can do almost the same argument as we did in the case of J running over all integers. So we can write the answer outside. And so to get rid of the co-primality condition, we can split into progressions. So let's say J is A modulo W. Okay, so just split the J sum into different progressions, modulo W. And now what you have inside is the sum over integers in a progression. So it's not quite the mathematical regressivity theorem, but luckily there's a generalization of that, which mathematical regressivity and Tal proved. So a slightly more general version, where you can also have a congruence condition. So you can look at short sums of Liouville in a congruence class A modulo Q. You fix some indices A and Q, and you have the same property that almost all of these sums are small. And the proof is quite similar to, it's almost the same as the original mathematical recipe. Okay, and this we can directly apply here. So again, put, if you estimate this absolute values, then by the mathematical regressivity Tau theorem, you can bound this by what you want. So little O of x times. So the number of terms here is px divided by w, and then you have, but w we think of just as a fixed number. So multiplied by little of x times px. And there's the extra factor of log of px here as a normalization factor. And therefore, like when you take this into account, it's really literal log of x times the number of primes after px, which is what we wanted. So yeah.
You have mathematical tau, so this really all depends on Q.
Yeah,
Right?
yeah, that's absolutely right. Yeah, yeah, that's a good point. Yeah. So think of A and Q as being fixed. Yeah, that's what I said. Yeah. Okay, so this concludes the proof modulo the thing that I so far swept under Dirac, which is step 2. Are there any questions at this point? Okay. So now let's look at the it's decoupling, how we can decouple the variables and how entropy plays a role there. So this is the one that we still need to prove. Okay, so we were heuristically trying to say that, well, if the Liouville function and its shifts were independent of this congruence condition, then you could separate the variables. But if you just directly try to make that rigorous, the kind of assumptions you would require from the Liouville function would actually probably go beyond 2-point Schauer. I mean, if you had the full Schauer conjecture that all the correlates of Liouville are small, then you could indeed argue that these two things are independent, but that would be tautological and even worse than that, because it would require more than what we're capable of proving. So kind of if you try to input any property of the Liouville function here, you just return back to square one, that we don't know enough about the Liouville function to say anything about this. And therefore, the right thing to do is to generalize, not to use any properties of the Liouville function, just replace it by a completely arbitrary function and hope that you can use probability to say something about this. Okay, and this is exactly what Tau did. And this led to a more general statement that he proved, which I call the sampling inequality. Okay, so if you have any two functions taking complex values, unbounded, maybe it's divided by 1, and if you have any function p of x that tends to infinity slowly. So this is the part where we need p of x to grow quite slowly. So in the other parts, it wasn't too important. Yeah, but here p of x, think of just like double log of x or some very slowly growing function. So then, if you look at a similar average, but you just replace the Liouville function by f1 and f2 in the two occurrences. And also, let's not put a logarithmic average, because if we can prove something for the ordinary average, we can also prove it for the logarithmic one. That's by partial summation. Normalized by the double log p of x. So this is the rule of 1.
Is this expected to be true for larger P as well, or is it not like a?
Yeah, that's a good question. I think it should be. Yeah, it should be true for larger P. And Helmut and Rogerview had a paper recently last year where they gave a different proof of this of the sampling inequality, which actually didn't use entropy. And okay, so there's advantages and disadvantages. One of the advantages was that they could take P of x to grow faster.
How fast?
I think like e to the log x to some power, which is quite a reasonable speed. So much bigger than any power of log. And also they proved something more general. So they proved a kind of expansion property of a graph relating to this. This inequality. So a graph where you connect, so you have the integers as vertices, and you connect n and n plus p when p divides n. So you form this graph, and they prove an expanded property for this, which then implied this inequality. Okay, and also it was more quantitative. So also the bounds here were more quantitative, and that's how they proved the strongest quantitative bounds known to date for the 2-point Chow law, which is that they save the factor of square root of log of x.
Doesn't generalize beyond, their argument doesn't generalize beyond 2.
Yeah, that's the disadvantage, that their argument only worked for 2-point correlations, whereas this theorem actually is equally well true. And with the same proof, if you use the Taos proof, if you put k different functions here. So you can put f3 of n plus 2p, so on, fk of n plus kp.
Does it get a hypergraph instead of a graph, or what do you get? Like what?
Well, the entropy doesn't somehow distinguish between these two.
No, I understand.
Oh yeah. They would need an expansion of some kind of hypergraph, which would be more difficult. So at the moment, it doesn't exist such an estimate. And yeah. Okay. Also, the entropy proof is shorter than the proof that they had. So there's advantages and disadvantages to either proof. Okay, but we note that if we have this theorem, then we can prove we can couple the m and p variables, because the logarithmic weight here is not important. Okay. So maybe let's have a break of 10 minutes at this point, and then I'll discuss how to prove this final key statement. And if there are any questions, feel free to ask.
Is there like some sort of deep philosophical reason that you can't just use Cauchy-Schwarz for this sort of thing, that you need something like entropy or hypergraphs or graphs? Can you?
Well, okay, so things like Cauchy-Schwarz would work if you had only one function here. So if you didn't have the f2, so if you only had f1, then this would be essentially a dual version of Turanko-Bilius inequality, which can be proved by L2 method, so like the second moment method. So kind of things like Cauchy-Schwarz. So it works for that, but okay, so that method doesn't work for the case where you have two functions. Well, basically because it's a much more complicated function of two random variables. So if you only had the f1, And if you apply the second Neumann method, essentially you would just have to understand the correlations of this random variable, so the indicator p divided n for different p. And these are of course independent. So p divided n is independent of q divided n for different parameters p and q. So that will be sort of the only input about the random variables. But here we have a much more complicated random variable. So I'll tell more in a moment, but you kind of need to understand the full sign pattern of f1 and f2 on the interval from n to n plus p of x.
Yeah.
And how that interacts with the p divided n. So when you have such a more complicated function of the random variables, things like the second Neumann method don't seem so easy to apply. Rather, you need something like entropy, which tells you more about like sort of arbitrary. If you have an arbitrary function of two random variables, if you can control the entropy of the information between these two random variables, then you can say something about the arbitrary function.
Mm-hmm.
I think the hyperparameter argument uses some extra properties of multiplication. So is it true for arbitrary functions?
Yeah, that will also, yeah. Any
You could imagine that there might be something better you could say if you do use some in a different clever way. The fact that you are looking at the double correlation of multiplication function somehow.
Yeah, it should be true with much better balance. I think it should be true with quite good balance. But the only way I could actually make such a conjecture is by referring to Chowder's conjecture, which we don't want to do, but yeah.
It's not valid for any collection of functions.
Yeah.
So just for
But for the case of arbitrary functions, the error term is not going to be super great. In fact, even for just if you don't have the f1, so you could say something like, so if you don't have the f1, f2, then this would be Turku-Bilius, and the saving there would be like something like log of p of x.
So if you assume Chowder, you can get p of x to be like x or x to the f.
Yeah.
Okay.
Yeah, basically, yeah. Yeah, so this would be, you're absolutely right. This would be true much more generality that p of x can be almost anything, and you have some quantitative bounds here, things like that.
Are these estimates worked out for function fields?
No, I don't think anyone has worked out for function fields. I suspect that similar methods could be used, but no one has done that. Okay, I guess we can continue. Okay, so how are we going to approach this? Sampling inequality. So as already mentioned, sort of L2 methods, or like the second moment method, are not going to work for this. And we need something else. Okay, I'm going to give a sketch proof of this, but not all the details. There's some technicalities that it's better not to write everything on the board, but I'll give you the main ideas of this proof. And there's sort of 3 steps in this argument. So the first one is to interpret this as a problem involving random variables. Okay, so we want to reduce this to RV, so random variables. And more specifically, that the expectation of a certain function of 2 random variables is small, which is basically asserting some kind of weak independence between those 2 random variables. So I'll tell you in a moment what the random variables are, but they have to do with the sign patterns of these functions, f1, f2, and with the divisibility conditions being the other random variable. Okay, and the second step is to, well, you want to further reduce this property of random variables that you want to prove to abound on the information between the 2 random variables. So I'll define later what I mean by this. What is the mutual information between 2 random variables? And the third one is to actually prove this information bound, that you have a good bound on the information, mutual information between 2 random variables. So that's one notion of sort of weak independence of 2 random variables if the mutual information between them is small. So prove a bound on the information. Okay. Let's start with step 1. So that's essentially just manipulating this expression to something that looks more like a function of 2 random variables. And just to simplify the proof a little bit, let me make a few assumptions. So let's assume in the proof sketch that f1 and f2 are the same function, and that f takes us +1, -1 values. And let's also assume that we want to prove a slightly weaker claim where we just claim that you can do this at 1 scale rather than averaging over all the scales. So let me prove a slightly weaker statement. So if p of x tends to infinity slowly, then there exists h less than p of x. H also tends to infinity, such that if you take the dyadic sum around h, that one is small. So the original claim was kind of saying that this holds for almost all scales h. If you have this for almost all scale h, then you can sum over the different scales and get the full sum up to px. Okay, all of these reductions are, they don't take much away from the general proof. So the general argument is similar, just to simplify notation and things we're going to make these assumptions. Okay, so now we are looking at the
Normalization or?
oh yeah, I think I do. Let's, for example, put multiple of the trivial bound. Yeah, and there should have been 1 over x previously. So x times number of times up to h. Thanks. Yeah, so we want to beat the trivial bound just by little of 1. That's fine. Okay, so first let's open the absolute values. So if we have absolute values, we can just take the absolute values away if we put a sign factor there, which represents the sign of the absolute value. Now our 2 functions are the same. So by introducing a suitable unimodular sequence, you can get rid of the absolute values. In fact, we don't even need the absolute values for the actual application to label, because there we didn't have the absolute values. But so you can just think of CP as 1 if you like, but it won't matter. Okay, so let's introduce an extra average here. So let's average over J and shift the average by J. To average, so to your page. So this is near to the middle of but okay, so what I did here was just if you make a sense of variables on this sum of m plus j, if you call m plus j equals m, then your m goes up to x, and you count every integer with the same weight, essentially. Okay, so you can, if you have a long average like this, you can write this. You can put a short average inside that, and it's the same thing. Okay, so that's a technical thing you can do. And now, okay, so this expression, let's just change the order of summation and write this as like this. And okay, now let's just put this as an average. So let me put an expectation here. So I just mean the sum of n up to x divided by x. Just to suggest more that we're going to use probability here. And this inner expression, we now want to interpret as a random variable of n. So think of n as being a random variable that we are, and the corresponding probability measure is just a uniform measure on 1 to x. And so what we have here, we have two random variables of n that play a role. So we have what I call x of h. So the sign pattern of f h. So this is taking values in -1 + 1 h. And I have another random variable, which is the conditions n modulo p for different primes p. Okay, and I claim that the so n we think of as the random variable, and so these are random variables of n. And I claim that if you know what x of h is, and if you know what y of h is, then you can compute this. In other words, this is a function of x of h and y of h. So that's just because, so what values of f do we have here? So all the values of f that occur here are between n and j plus p is never bigger than h. So it's something between f of n plus 1 and f of n plus h. And the divisibility conditions, they are modulo to primes p from this range, h/4 to h/2. Okay, so this means that the inner sum must be some function of these two random variables, because that's all you need to compute the value. Okay, so we can write this as some function of x of h and y of h, where this function, so it's not really too important what the function is, but so if x is taking values -1 + 1 to the h, and y is taking values the product of these z mod pz, or those values p, then this is that's the sum of now we have x of j plus p, p indicator, p divides y plus j. Okay, so if you just substitute x of h and y of h to this expression, it gives exactly what we had. Okay, so this achieves step 1. So we've reduced the problem to understanding two random variables, which we believe to be independent, and if we had, if these were generally independent, then you should be able to show that this is small. but we cannot show that these are generally independent. But we can show something weaker, which still suffices to control this kind of expressions. So if you know the useful information between X subbase and Y subbase, which I'll define in a moment, so if you have bound on that, then you can control these kind of expressions. So that's going to be step 2.
So the mean of these variables are for y it is equal to 0 or it's close to 0 or
Yeah, exactly. Yeah, it's equal to 0 if if y is taking values modulo p. Or rather, this y is taking values in it's a product of groups. Yeah, so the mean is 0. That's exactly the point. Okay, so now we come to step 2. So here the main claim is the following, and I won't give the full proof of the main claim, just some sketch maybe of it, but the claim is that this expression of the function of X subbase and Y subbase can be bounded in terms of the useful information, which I'm going to define. So it can be bounded in terms of the useful information plus something small. Okay, so if this information was small, then this will be bounded by epsilon, and that's what we want. Okay, so there should be a normalization, I guess, because this sum has size h/2. So I guess we really want to normalize everything so that they have mean 1. So just factor out the phi of h, so that that's mean 1. Okay, so this is going to be the claim in step 2, and the claim in step 3. This is claim 1, this is claim 2. So the claim in step 3 is that you can bound the information. So there exists infinitely many h, so arbitrary large h. Such that useful information is literal of h over log h. Okay, well, if you just postulated these two claims, then the conclusion would immediately follow, because this is saying that this term is literal of 1, so it's less than epsilon. So the whole thing is less than epsilon, and therefore you have cancellation in the average of x and h, x and y. Okay, but now I need to explain what information means. Okay, so first, to define the information, we need the notion of entropy. So if x is a random variable, let's say that's y and x and y, random variables, which have finite ranges, so then the entropy of X sum of the probabilities of the values of X weighted by this function. So the function t log 1 over t, where t runs over the different probabilities of the events x equals x. Okay, so that's entropy of a random variable. You can generalize this to conditional entropy. So if you have two random variables, the conditional entropy of X given Y is the entropy of the pair X comma Y minus the entropy of Y. So the pair X comma Y is another random variable which takes values in a bigger space. So you can just apply this definition to compute it, and you subtract the entropy of Y. Okay, so that's the conditional entropy. And finally, the information, the mutual information between X and Y. So this is mutual information is equal to the entropy of X minus the entropy of X given Y. And also, you can check this is equal to, it doesn't matter which way you take X and Y, it's also the same if you take entropy of Y minus entropy of X. Okay, so this information kind of represents how independent these two random variables are. So if X and Y were completely independent, then the information between them would be 0, because the sort of new entropy so if X and Y were independent, then the entropy of X given Y would be just the entropy of X. There will be no new entropy, or there will be no decrease in the entropy from that. So this is a quantity that's 0 if X and Y are generally independent. And on the other hand, the biggest that this quantity can be is the minimum of the entropy of X and the entropy of Y, because the entropy turn out to be positive always. So, and that case would happen exactly when one of the X and Y is the deterministic function of the other one. Okay, so information 0, X and Y are independent. It's always less than equal to the minimum of P. Now, let me state a couple of properties of entropy that we're going to need for proving these two claims. Okay, so a few facts about entropy. First one. that the entropy is always between 0 and the logarithm of the size of the range. Okay. Another property is the sub-additivity of entropy. You have the entropy of the pair x, y. So this random variable is always bounded from above by the entropy of x plus the entropy of y. And you have similar bounds for the conditional entropy. So if you have the conditional entropy of the pair xy given a third random variable z bounded by the conditional entropy of x given z and y given z. Okay, so these properties, I'm not going to prove them, but they're not difficult to prove. So the proof essentially uses Jensen's inequality. So for example, this upper bound of the entropy being less than log of the size of the range. You apply Jensen's inequality to the function that appears in the definition of entropy. So T log 1 over T, you apply Jensen's inequality to that. And what comes out of that application is exactly this bound for the entropy. And the others are also proved using Jensen's inequality. Okay. Yeah. Okay, so let me say a few words about the proof of claim 1. I won't give the full proof. So claim 1 is based on 2 probabilistic inequalities. So one of them is concentration of measure, and the other one is what's called Pinsker's inequality. So let me write down Pinsker's inequality. Rather, it's a certain variant of Pinsker's inequality, a special case of the more general statement. But this states that if y is a random variable, some range R, a finite range, and if U is a uniform random variable with the same range, then if you want to understand the probability of y belonging to a set, any set, you can bound it in terms of the entropies. So this is how the entropies arise. Divided by log of our probability U. Okay, so this is true for any random variable y, and U needs to be a uniform random variable on the same space. And the proof of this is just a manipulation involving the properties of entropy stated there. So nothing too deep goes into the proof of that. And so this inequality we want to apply to so what we want to understand is the probability of this random variable being bigger than epsilon. So if we can bound the probability that this is bigger than epsilon by epsilon, well, we want to bound this in terms of the information, like over there in claim 1. But it's difficult to do it directly because we don't really know how x and y interact. So let's instead initially look at the probability if you fix the xh. So if you fix xh to have a given value, so okay, so if you fix some element in the range of xh, and you look at the probability that is large given the value of x. So the point is that the y sub h we understand quite well. So it's easy to understand n modulo different primes. Those divisibility conditions are independent by Chinese Meridian theorem. So the y sub h behaves very much like a uniform random variable.
So we don't know the joint distribution, but somehow we can say something about 1 over the projection, right?
Yeah, exactly. Yeah. We don't know about the joint distribution, but we can say about the conditional distributions. So to this, you can apply Pinsker, and what it gives you is that you can bound this by, so U sub h is a uniform random variable on the same space as YH. So range of UH is the same as range of YH, and UH is uniform. And now the probability, so we replaced y by u, so the genuinely uniform random variable. Okay, so this is applying Pinsker. And okay, so this probability where we have the genuinely uniform random variable, for that you can use concentration of measure. Because the f function that we have here, it's a sum over different primes of random variables that only depend on n modulo p, which means that it's the sum of now if we have the user base instead of user base, and if we've also fixed the pattern of X, so it's just a fixed pattern, then it really is a sum of independent random variables. So for every P, we have an independent random variable. So it's a sum of independent random variables. And you can use concentration of measure to bound the probability that that is large. Okay, so if you apply concentration of measure, you can prove that probability essentially speaking is there's an exponential decay on the probability. So absolute constant. So we have roughly h over log h random variables in our sum. And there's an exponential tail bound on the probability that the random variable is epsilon times the maximum. So if epsilon is fixed, this is an exponential decay in the probability. And if you input that here, you get the epsilon squared h over log h factor, which we have in claim 1. And then we just need to understand the expression in the numerator. So let me say about entropy of this one. And okay, rather first you want to input this. So epsilon squared h over log h found here from concentration measure.
So this is VH, so it's somehow it is related to this uniform distribution.
Y sub h, yeah.
No, V.
U.
It's you, the uniform.
Yeah, that's
This uniform.
yeah, this is uniform, yeah. UH is generally uniform. Okay, and so now we can express this probability, so the original probability, in terms of these conditional probabilities. So that's by using Bayes' formula. You can write this as a sum of these with the weights of probability xh equals x. So we can bound the original probability by and if you think of it for a while, what you get is the so when you sum this weighted by probability of xh equals x, and you sum over x, you get the conditional entropy of ys given xh. Okay, and now we just need to manipulate this expression to something like the information. Okay, so the conditional entropy, if we compare the definition of information and the definition of conditional entropy, we can write this as here. size of H plus the information of X of H, Y of H. Just by definition. And so the key point is that Y sub H, so the N1 P conditions for different primes P, they are extremely close to being independent by Chinese Meridian theorem. So YH is very close to being uniform. So you can write the probability of YH being in some set E. That's essentially what you get for a uniform random variable. Plus a small error from the fact that we look at only integers up to X and not all integers. But the error term is very small. It's like this. So this is from the Chinese Meridian theorem. And now here you need H to be small. So in particular, P of X in the theorem needs to be small so that this product is nowhere near X. So this term is something small. This H is less than PX. And that goes to infinity slowly. So Y sub H is very close to uniform. And therefore, you can prove that the entropy of U sub H and Y sub H is almost equal. So this part you can bound by.
It's just log of the cardinality of direction.
Yeah, I mean that's the upper bound, but you need to compare the individual probabilities. That all the individual probabilities for U and Y are almost equal, and therefore the entropy is by continuity almost the same. So this term is something very small, and therefore you're essentially left with such the information, and that gives you the first bound.
So this is the only place where the restriction on H comes from, and how YH is uniform?
You mean the size of H?
Yeah.
Yeah, it comes from the second claim, which I think.
Also, so here, how large? Also from this restriction, from the uniformity.
Oh yeah, the upper bound. Yeah. Actually, yeah, this is the key point that so the product of primes up to H is e to the big O of H. Essentially, so you need e to the big O of H to be less than, let's say, square root of X to have a comfortable margin. So that means that H needs to be certainly less than a constant times log X. Yeah, so that's the reason why H needs to be small, that these things are generally independent. Okay, I think I'm.
It shows up also in the other.
Yeah, here also. So this is just
it's
yeah.
So the same reason. So the problem is how uniform is Y.
Yeah, or here rather the reason is that so we can only prove this for a certain set of H. Which comes from the pigeonhole principle. So it's not for all H, and it's that in every long enough interval, we can find a good value of H.
But that also requires a restriction on the size?
Yeah, because the good intervals, they all need to be less than this. I mean, they need to be within 1 to X. So you need quite long intervals of H where you can find one good value with this property. So that
I'm
limits
just trying to clarify this condition on H being a constant times log H. Is it weaker in claim 2, or is it the same in claim 2 as in claim 1?
It's the same. So yeah. If you work out the dependencies carefully, essentially you just need H to be little of log X, and then everything works. All the claims work with that assumption. So.
But you still need little of all.
Yeah, you need
for claim 3 as well.
Yeah, I think if you formulate it, yeah.
But for a different reason, that's what I'm trying to understand. I'm trying to understand.
Yeah, so. Okay. I think rather it's just this where the limitation on H comes from, and not the other one. Okay, so I'm out of time, so I'll say a couple of words about claim 2. So this proof, it's a manipulation of the entropy inequalities. So you look at the what you can call mean entropy. So the entropy of xh divided by h. And you relate this to the entropy of x sub kh over kx, where k is a natural number. So by applying the sub-additivity of entropy several times, you can relate these two quantities. You get an inequality between them, and the so in particular the you always get that the mean entropy is decreasing when you. So if you take a bigger value of h, let's say k times h, it's always decreasing, and the amount of how much it's decreasing depends on the information. So applying the properties of inequality of entropy stated on the board, you can prove this kind of inequality. So the mean entropy, this quantity, at every step, it decreases by the amount of information. So if we assume that the information is large at every scale, then at every scale, this mean entropy is sorry. It should be the other way around. The mean entropy is decreasing by log h, 1 over log h, but it cannot increase indefinitely. You need to do a certain summation there because it's not increasing by a fixed amount, but rather by 1 over log h, essentially. But if you then sum this inequality over different values of h, and it telescopes. So if your next value of h is k times h, you get a telescopic sum. So these mean entropies cancel out, and you just get the bound on the sum of 1 over log h. And essentially what you need at the end is just that the harmonic sum diverges. So the a's are growing roughly exponentially, the values of h that you take here. And so if you had this inequality with the information being large for every value of h, then you could sum it. And by telescopic summation, these mean entropies would cancel out. And you would just get a sum of 1 over log h, which would be too large. It would be something tending to infinity, whereas the other side would be bounded. And that's a contradiction. So it's just a few lines of calculation involving the entropy inequalities to check this. But this is where the name entropy decrement comes from, that you're decreasing the entropy at every stage until you get a contradiction. Okay, but I think those are the main ingredients of the proof. Yeah, that's all I wanted to say.
Yeah, you just took away my question, maybe why it is called entropy decrement.
Yeah, that comes in the final step.
Yeah.
So to which kind of functions it applies? Multiplicative functions.
No,
Any function, any bounded function.
Any bounded function?
Yeah. Yeah, so this was the sampling inequality, and you kind of wanted to get rid of the multiplicativity because it was somehow blurring the picture that you don't actually want to use properties of multiplicative functions if you're trying to prove something probabilistic. So it was a completely general.
I think it's like the point is that independence between addition and multiplication, like this lambda n plus p, and p divides n. That's kind of the, or lambda or a some function that it's not the functions that matter, but this operation of multiplication and addition.
Yeah, so such sign patterns are always weakly independent of such divisibility conditions.
Any more questions? Thank you again. Thanks a lot.